Okay, so get this. You know how our brains are these crazy complex things?
Right.
Well, they basically run on the same power as like a dim light bulb.
Yeah, just a few watts. Wild when you think about it. All that processing, learning, even dreaming.
Meanwhile, we've got these giant AI models sucking up energy like nobody's business.
Some with the carbon footprint of a whole city, it's true.
Makes you wonder if we're going about this AI thing the wrong way. What if instead of just making them bigger, we looked at how nature does it, you know?
That's precisely the thought behind Professor Alex Oria's work. He's all about mortal computation.
Mortal computation. Okay, now that's a new one. Sounds kind of ominous, doesn't it?
Maybe a little, but it's not about AI dying or anything like that. It's more about recognizing that these systems, to be truly intelligent, got to be intertwined with their physical form, just like us living beings.
So you're saying it's not just about the code, but the actual hardware too.
Exactly. The physical stuff, the processes within it, they're all connected, can't separate them. That's how biological systems are so efficient. And it ties into this drive to keep going, to survive.
Makes sense. Our brains are constantly trying to maintain a balance, right? Like stay stable even when everything's changing around us.
Precisely. And Professor Oria argues that this drive to persist is key for building AI that can truly adapt and be resilient. Instead of just focusing on, say, winning a game, what if AI was designed to keep learning, to constantly expand what it can do?
So more like embracing the process of learning itself rather than chasing a specific goal.
Exactly. And that's where the niche concept comes in. Just like an organism evolves to fit its environment, a mortal computer needs its own digital space, a niche, to shape how it develops.
So the environment becomes a part of the learning process. That's fascinating, but what does that even look like for a computer? Are we talking like a digital terrarium?
Think of it less like traditional programming, more like, well, teaching. We don't give a child a manual on how to be a person, right? We provide an environment, let them explore, offer guidance along the way. Same idea here.
But we're not talking about teaching simple tasks, are we? We're talking about replicating learning and development itself.
And to understand how that might be possible, we got to zoom in on the building blocks. Cell.
Hold on. Are you saying my brain's just a bunch of tiny computers?
Yeah.
Because that's not a comforting thought.
Not quite computers, but you can picture each cell as its own system. It has this boundary, this Markov blanket, as Professor Oria calls it, separating what's inside from the outside world.
Okay, Markov blanket, you've officially lost me in the jargon.
Think of it this way. Your cells are constantly taking stuff in, getting rid of waste, trying to stay stable, but they're also part of a bigger system. The Markov blanket is like a representation of that boundary between the system and everything around it.
So it's like a filter, helping the cell maintain order while still interacting with its surroundings.
Exactly. And here's where it gets exciting. These Markov blankets, they can be nested.
Yeah.
Cells make up tissues, tissues make up organs, and boom, you've got the whole organism. This, Professor Oria argues, is how complex self-organizing systems, maybe even intelligent ones, could emerge.
Whoa. Okay, so we're scaling up from a single cell to potentially a machine that can actually think and learn. Mind-blowing, really.
And it's not just about the structure, but the processes. How do biological systems learn and evolve? Professor Oria's got a framework for that. MILS.
Let's hear it.
Mortal inference, learning, and selection.
Mills, Mortal Inference, Learning, and Selection. Has a nice ring to it, I gotta admit. So how does this Mills thing actually help us build these mortal computers?
Well, it tells us that biological systems, they don't just learn on one time scale. It's all intertwined. Think about how your brain processes info in a snap, recognizing someone's face, for example.
Yeah, I don't have to, like, study a picture for an hour to know what it is.
Exactly. That's the inference part of Mills in action.
Yeah.
Real time making sense of the data.
Got it, so that's inference. But learning, that's more about connecting the dots, right? Like when I learned guitar, took time, practice, all that.
Absolutely. Learning is recognizing those patterns, updating your brain's model of the world. Happens on a slower scale than just reacting.
Okay, so if inference is reacting and learning is understanding, where does selection come in?
Think about those guitar lessons again. While you're learning those chords, your brain's actually making some connections between neurons stronger while others fade away. That's selection. Your brain's literally rewiring itself based on what you're experiencing.
So it's not just what we learn, but how our brains physically change. That's wild. But how do we translate that to AI?
Professor Oria would argue that most AI today, especially deep learning, it's stuck in the learning phase, good at recognizing patterns, but
Like a student who aced the memorization test but doesn't really get the material?
Perfect analogy. And that's where Mills gets interesting. It pushes us past just pattern recognition toward AI that can do that real-time inference and even change its own structure through selection.
So instead of just being fed data, this AI would interact with its environment, learn, and grow on its own. Sounds almost impossible to program.
Which brings us back to teaching. Instead of rigid rules, we create an environment, that niche, where the AI can experiment, mess up, learn from feedback.
Like giving a kid a playground, not just a textbook. Way more fun, too.
Exactly. But it's also where the challenges pop up. How do we teach this way? What kind of feedback helps these systems actually learn in the right direction?
It's almost like we're talking about raising AI children now. But before we go too far down that road, we did touch on some practical hurdles too, right? What are some of the big ones?
Hardware is a huge one. Our brains are great at parallel processing, doing tons of things at once. Traditional computers, not so much.
Like trying to run a video game on a calculator from the 80s, just not going to happen.
Pretty much. We need new types of hardware, neuromorphic chips, designed specifically for this kind of bio-inspired computing. It's being worked on, but it's early days.
So hardware's one thing. What about the software side?
Another hurdle. Even with the perfect hardware, we need the right tools, the right programming languages to build and train these systems. Imagine trying to build a skyscraper with just a hammer and nails.
You're really driving home this point about needing better tools.
But the good news is, people are on it. Professor Oria's team is developing software like NGC Learn, making working with bio-inspired algorithms easier. Lots of challenges, but tons of excitement and progress too.
That's good to hear. But let's zoom out for a second. We've talked about the how of this biomimetic intelligence, but what about the why? What's the end goal? Just smarter machines, or is there something more?
Yeah, I mean, it does feel like we're going beyond just, faster calculations or whatever. It's like we're trying to crack the code of intelligence itself. Exactly. It's not about perfectly copying the brain, but understanding those core principles that could lead to, well, intelligence in any form. Biological, artificial, who knows what we'll come up with.
So it's almost like a philosophical question too, right? Are we just really complex machines ourselves? Or is there something more to consciousness than just a bunch of neurons?
Big questions, ones philosophers have been debating for ages. And now with biomimetic intelligence, we're starting to tackle them from a scientific angle.
It's kind of wild, like science fiction becoming real. We're not just building machines, we're blurring the lines between what's artificial and what's alive. Exciting, but kind of freaky too,
For sure. And that's why we got to be careful, thoughtful about this whole thing. It's not just the how of building this AI, but the why that really matters, especially when it starts to mirror life itself.
No doubt. Well, you've definitely given us a lot to think about today, from like how amazingly efficient our brains are to this whole mortal computation thing that could totally change how we view AI. But I think the biggest takeaway is we're just getting started here.
Absolutely. This is just the tip of the iceberg when it comes to biomimetic intelligence. Who knows what amazing discoveries are waiting for us as we dig deeper.
A future full of possibilities, that's for sure. And on that note, we'll leave you with this thought. If we do manage to build AI that learns and adapts like life does, what's that going to teach us about ourselves, about our place in the universe? Thanks for joining us for this deep dive, folks.